So I'll give you a little bit of background just kind of on how this came about, the technology itself, the company as well. Entrepix Medical is the name of the company. Planatome is the technology itself. So we spun out, Entrepix Inc. is the semiconductor side of the business. We've been around since 1998. We incorporated this technology, this what we call chemical mechanical polishing in the semiconductor world. We patented it and trademarked it for medical use as the name Planatome. So whenever you see Planatome, that means we've taken that polish process and applied it to a Planatome scalpel or a Planatome endocutter or Planatome scissors. We're starting with the scalpel, but so when you see Planatome, that means we've polished it with the same semiconductor process. So the parent company, Entrepix Inc., we are, even though we're a small company, we started out focusing on this one process. It's the most recent of those developed to make chips, and chips are made on wafers. I don't know if you've ever seen them, but the chip manufacturing process, and I've got a quick video to show it to you. This is the chip manufacturing process right here, and there's a ton of different steps, and each one of them, when you're going to make a chip, is used, could be multiple hundreds of times. So the way we make chips is we take, and I'll pass this around so you guys can see it and take a look at it, but we take a bare silicon wafer. You hear about chips all the time, right? So that's what it starts out as. Matter of fact, even that initial finish is done with CMP. And then we start putting on different layers and pattern it, and we pattern it with light. So, and then this is what it looks like. And then what happens is then they saw these up, and each one of these little squares is a chip, and it gets put into this little, like a package, and little wires get hooked up to it. So it's incredibly precise technology, and this little video we have, we'll show it to you and give you an idea of it. So, but feel free, I'll send this around here. If you look in this, you'll see.
Does this make my car run? No.
Yeah, as a matter of fact.
Yeah, one side in the water.
Yeah, as a matter of fact. So you can see inside that little window there, that tiny chip, and then take a look. There's little wires that connect to a certain point on there. They go to each one of these little leads when they plug in, and you make all sorts of different things. It's remarkable. Yeah, it's crazy when you think about it. So, but pass it around. So if we look at the surgical blade, you've seen these. This is actually the exact same blade. You can see we buy them from Swan Morton. It really doesn't matter who our suppliers, but these ones are. You can see the SM right there. The way they make surgical blades, and it was the disposable surgical blade was first patented in 1915. It's a stainless steel blank, and then there's two diamond grip wheels that just grind it right up to a point. And you can see, you'll see this. You can see if you look at this. So now, if you look at the edge of each one of these are scanning electron microscope photos. This is 1000x. You can see a standard scalpel, and this is what the edge looks like. So we're looking at the side profile here versus ours, and this is the exact same scalpel. So we don't manufacture the scalpel from scratch. We buy them like this. We polish them, and then we send them back through sterilization packaging, with their own name on it. So when you compare these here, this is literally the same one. If you're to look at, so if you look at the peak to valley roughness that's in here, it's on the neighborhood of 5,000 to 50,000 nanometers. Just to put some reference in there, human tissue cells are about 10,000 to 100,000. When we're done polishing it, it's 5 to 20 nanometers. So it's a remarkable difference, multiple orders of magnitude. So it's essentially 1,000 times more precise because you don't have things going in lots of different directions. It is just one. So, I mentioned that the scalpel was invented in 1915. That's the disposable scalpel. The scalpel technology, actually grinding to get the edge that gets cut, you can go back to Roman days, and it's pretty much that. So really, the biggest invention was the fact that they made it disposable. And then in 1920, the patent was for the stainless steel in the scalpel. So if you look at technologies and how they evolve, it's always done in 4 stages. So just for a comparison standpoint, I should look at, let's use the telephone right about this same time frame, right? It was invented. So if you go forward after the early stage innovation, you've got rapid product evolution, and you can see what the phone's doing, and then you fully develop it and refine it, and ultimately you completely reimagine it, right? Completely reimagine, disrupts the market. Well, if you look at the scalpel, there was nothing Nothing for 100 years until now, when we have the Planatome, where we apply our semiconductor technology to it. So again, I mentioned that it's patented and trademarked as Planatome for use in the medical industry. Chemical mechanical polishing or planarization, that you can use them interchangeably, is what we call it in the semiconductor world. So, and in the semiconductor world, we take it actually even down to an order of magnitude finer than what we showed you here. So the parent company, we specialize in that. We put up the world's first, even though we're small. So I say this with all humility. We put up the world's first R&D all around the CMP because it's incredibly complex. There's a lot of different variables. We have the biggest portfolio of CMP processes, no matter what the material is, anything from hard to even semi-hard, some polyimides and stuff, that we can polish so it's perfect, almost perfectly atomically smooth. So that's how we started looking at this, saying, well, what other industries could benefit from that? Where can we take this technology? It was actually our CFO. He's like, we all these companies right here, these are all our customers. He's like, here we are, this small and Trepex, but we are working with Apple and Intel and you name it. What else can we do? How else can we monetize it? So that kind of got us thinking about it. But, so if you look real quick, this is where we polish the wafers. You'll see that in this video. We wanted to give you guys a sense for, not going too far in depth, but just to understand how much technology is in making the chips themselves. This chip right here, which was one of the Apple microprocessors, this one had 10 billion transistors in that little microchip right there. The latest generation now, this was probably about 4 years ago, the latest generation now has up to 50 billion transistors in an area the size of your fingernail. It's remarkable. And you'll see a picture of the very first transistor ever, and it was made in Bell Labs. It's like this big. It's crazy. But you'll see it in this video. And they'll talk about the technology. They talk a lot about when we put those patterns down, it's done with light, but you'll see it. It's really pretty cool stuff here, I think so.
Human ingenuity. Since mankind first realized that harnessed electricity can light up the darkness, the world has been on a remarkable journey of advancement, changing virtually every aspect of our lives and how society functions. The advent of the electronics era began with Bell Labs' invention of the world's first transistor in 1947. Driven by the spirit of ingenuity and innovation, scientists transformed this breakthrough discovery to radically enlighten our understanding of what is possible. One transistor made with simple wires and large components exploded into today's semiconductor electronics, which are technological marvels containing up to 50 billion transistors in a single computer chip the size of a human fingernail. Semiconductors are the most expensive innovation in the history of the world and require a level of manufacturing precision that is inconceivable to most who rely on their vast computing power. One state-of-the-art manufacturing plant can cost in excess of $20 billion. Leading-edge chips contain tiny transistor lines that are 15,000 times smaller than the width of a human hair. These tiny lines are created using highly modified UV light produced by the world's most complex piece of equipment which ships by 3 fully loaded 747 cargo planes, contains some 100,000 parts, weighs 200 tons, stands 3 stories tall, and costs $200 million each. Manufacturing at this molecular scale can only be accomplished if the surface of the chip is first precisely smooth and defect-free. The technology chip manufacturers use to create this level of surface precision is called chemical mechanical polishing, or CMP. Millions of dollars have been invested adapting CMP to provide the same molecular level precision to surgical cutting instruments. We call this adaptation Planatome. Throughout history, innovative dreamers and doers have skillfully employed proven methods from other industries to advance their own. There has been no innovative change to the surgical blade in more than 100 years, until now. A Planatome blade has the most advanced cutting edge ever conceived. It is over 1,000 times more precise than a conventional blade. dramatically advancing the standard of care. Planatome provides extraordinary healing and incision benefits to both patients and surgeons. Planatome. We didn't invent the scalpel, we perfected it.
So that'll give you an idea of, I mean, if you think about that, to build one manufacturing plant, it's $20 billion. Each piece of equipment for putting down the pattern are $200 million. The next generation one would be $300 million. Okay, so when, Deb, you made this comment to me about just yesterday or the day before, that no matter who you talk to, whether they're medical professionals or even just the random person you find on the street, everybody understands it. The concept is really simple and intuitive, right? We're taking something from one industry, moving it to another. But essentially, we take a blade that has those defect sites on it. We get rid of the grind defects. So if you have no grind defects, you have no microtearing. No microtearing, reduce trauma. The way we simulated this was with a piece of cheesecloth, and the fibers here are supposed to kind of represent like the extracellular matrix fibers. But you can see how a standard scalpel grabs it, rips it, snags it, tears it, right? It catches on to all those little serrations, essentially, that are sticking out. Where with ours, it goes through, and it's much more like a paper cut instead of a saw, like slicing instead of saw. So if you have then reduced trauma, reduces its swelling, and that's what creates, well, we have incredible precision because of the level of surface roughness on the blade, but then dramatically improved healing methods, which you see. All adhering to Halstead's principles, very, very largely in line with those. And you could even probably get the blood supply. You'll see a picture, I think it might even be in the next slide, where there's a big difference even just in 24 hours with a standard scalpel versus ours. So, okay, so you guys have seen this picture right here. This is 1000x. If you do take this exact same thing, we just drill right into 5000x. So here's what that looks like at 5000x. And then here's ours at 5000x. So that, again, is looking at the side profile. Now if we look straight down onto the cutting edge, so now we're looking at the top of the V right here. Here's 1000x of a standard one, and you can see the diamond grit here and then here. And they actually, this is Swan Morton's, they actually put more on one side specifically for the tactile feel. So the surgeons feel the click, 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 and they know, okay, I'm cutting through, I'm cutting through, I'm cutting through. But that click, click, click is it grabbing those fibers and ripping them out, at a micro scale, cellular scale, instead of just slicing right through them. But again, nobody's ever thought about it because you're talking about a dollar scalpel. Who puts money into a dollar scalpel? And the only reason we did is because we already were doing this in the semiconductor world, right? So if you then take this and look at it at 5000x, you look at that and you go, oh man, that's remarkable that that's actually what's cutting. And we didn't go around looking for the worst blade for these pictures. Swan Morton is the #1 blade in the world. So Bard Parker's the #1 in the US, but #2 in the world. And then there's a number of other blades, of course, as well too. And then, again, this is this blade right here, we polish it, and this is what it looks like when we're done. Same thing with each one of these. So one thing that I always found striking is as you go, with a standard blade and you change the magnification, the picture dramatically changes. But if you look at ours, it doesn't really matter the magnification. It's pretty much the same thing because we've wiped out anything that's an irregularity. It's in there. So then so you'll see some clinical and preclinical work. The animal work, actually both the animal work is largely done by Dr. Raphael Lee out of the University of Chicago. He's MD, but he's also a PhD, I think, biomedical engineering. So he's big into research. So they did side-by-side incisions on a guinea pig, and this is 24 hours after with histology. And this was what I was talking about with the bleeding, by the way. So side-by-side incisions right here, and you can see 24 hours afterwards. And this looks like more like a paper cut. You can hardly tell that there was a slice there. When this one here, there's lots of bleeding, more swelling, the wound's still open. From a histological standpoint, if you look at that, this was 10% wound closure and 90% wound closure. So this paper was actually published. You can get your copy of the paper. And then they also looked at it from the standpoint of the collagen deposition and the reorganization at day 7 and then day 180. And you can see with the Planatome blade here, it's much more uniform collagen. With the standard one, it's kind of a little red outline here, it's tough to see it, but is the collagen deposition from where the wound that was torn out instead of just sliced through. And then here it is 6 months out. So the other thing that they did is then to quantify that, they looked at the number of pixels that each one of these represents, and then you can see right down here, the polished blade, the size of the essential wound versus the standard blade. So.
The one thing that's important to understand is the method that they use for creating that specimen. Is once they made the incisions on the guinea pig, they sutured, and then they put stereotape over it. And then this one was taken 24 hours after incision. They euthanize the guinea pig. They take the sample, and then the sample that you see there is between sutures. So they cut a specimen out, between the suture points. So.
And they sutured this without tension, right? It was just to hold it
right
in place. So this is an IRB approved clinical study that we've done just relative to scar. So this was Dr. Aguyo out of El Paso, 25 page, 24.
We enrolled 28 and 24 made it to the
6 month mark and with all the pictures. So here's just a couple of samples from there showing the 3 month and 6 month mark, and this person came in at 2 months and 6 month mark, but the Planatome side and the standard blade side. These, by the way, were randomized from a standpoint of the pictures. I either just flipped it this way or this way, so you have all the Planatome. But in the study itself, it was randomized, which side they used, so it wasn't all left versus all right. So, and it was double blinded. This work here was done at the Asan Medical Center, which is at the University of Ulsan in Seoul. It's the #1 hospital, largest one in Seoul, and
or in Korea.
Or in Korea, excuse me. Yeah, they've got 2,700 beds in this one hospital. Here, this one right here is some work that they've done where they did a laparotomy. You see, it's a long incision here. They put a P for a polished blade and a B that was actually a Bard Parker blade. We used Bard Parker a long time ago, so the only difference in these two is the scalpel that was used, and then 8 weeks later, this is the difference in the scarring. And if you look up here, this is up top where the skin is in much more tension. The scar there would normally be worse just because of the location. And down here, where I still have my baby weight from supporting my significant other one, Sullivan, born. But you don't get quite as much of a scar down there. So that usually, a lot of surgeons resonate to that. So one of the other things that the doctors, Drs. Choi and Hong, in Seoul, they said, if you look at the difference in healing that we see just with the clinical case study work we've done, they thought this might be able to make a huge difference in diabetics. So what they did was essentially a 2x2. They had healthy rats and diabetic rats, and then a standard scalpel and our scalpel. I know there's a ton of information on this. This is information from a paper that was just accepted for publication. It's coming out in the Wound Healing Journal, I believe it is. These markers here, and I won't pretend to know what they all are or do, but I'm sure you guys know these very well. If you look at this data here, the important thing to note is the orange. If you always compare the orange to the green, and then this is just however many numbers of days, 3, 7, and 30. Orange to the green. Orange is a healthy rat with a standard scalpel. Green is a diabetic rat with our scalpel. Diabetics don't heal very well. In every one of these cases, it was better. The diabetic rat with our scalpel was better than, or at least no worse than, equivalent to, a healthy rat with a standard scalpel. So from a healing perspective, and I know they were very excited about it, and not just diabetics. They said these markers they thought would translate to a whole bunch of other comorbidities and stuff. So, Dr. King, I know when we were talking with you, you thought because it's so much more gentle in the cutting, even like the acid burn victims, because the skin is so compromised that you might be able to do things that you could never do before. Right. So this paper will be coming out. As soon as it is, we can get you copies of this one too. I think you actually have a copy of the original of the manuscript. So more work done by Dr. Lee. This is also a paper that is out. We can get for you here. Again, with the guinea pigs, they looked at macrophage density as it relates to pain. If you look at the macrophage density over time here, you can see a standard blade day one is about 6 times. If this is roughly the baseline, you've got this is about 6 or 7 times elevation of the normal macrophage, and we're significantly less when it comes down here, much more. I would try to explain this one, but TGF beta I only have briefly read about in the book, so I'll never that to you guys. But you can see the difference here for. With nerve regeneration, here's another one that they looked at. If you look at the electrical impulse conduction, this is a never cut nerve, so you can take that level of darkness of the brown, that's electrical impulse going through there. And then here we show the nerve as it's cut by a planatome versus a standard one. So you can see that this is obviously lighter than this, and then this is lighter than this, but how much? So if you quantify it, after 5 weeks, standard blade has about 10% recovery, and we're up at 25%. So at least according to Dr. Lee, he said if you don't get at least 20% within, some people it's as short as 5 weeks, some people it's as long as 8 weeks, that nerve will probably atrophy and die. So you've got to get it, or you're going to get, like I know I've got numb spot on my leg, on my hand, where I've had surgeries before, and that's what he said he attributed a lot of that to. Okay, so when we were talking before about when Dr. Shadran was talking about sharpness versus smoothness, I want to talk a little bit about it because the first thing that everybody thinks is, oh, you're sharpening the blade, but we're actually not sharpening. We're removing the defects and making it smoother. So, intuitively, we all have this concept of what sharp is from the time you're a little kid, right? You get poked with something, it's sharp, right? It goes right through real quickly versus something that not quite as much. So, but if you look at from a physics perspective, what is sharp? There's really no measure of sharp where you say, oh, it's a 3 sharp, it's a 7 sharp. There's no physical measurement for it. So, but conceptual is what we have. If it goes through, if I don't have to push very hard and it goes through, it's sharp. What are the attributes that really would create that feeling of sharpness? With the blade, it's 2 different things. So you've got the angle that the blade is at right there. So you can see that across the top. And then the shape of the tip itself, too. And this is where I was talking, with the CMP pads, they're a little bit compressible. So if you aren't careful, because the pad will be coming across here, but it could bubble out just a little bit here and I'll start bullnosing it. So what we did, again, we took a 6-axis robot, Fanuc robot, incredibly precise. And we have very specific pressures and times and placements for it as you're coming down to make sure we have this V as much as possible. We actually also took the angle in a little bit from what we receive it at, and for a very specific reason, to try to get it as close as possible to feeling like the existing one. And the reason why it would feel a little bit different, this next one is going to make perfect sense to you, right? The other things that can contribute to whether something feels sharp or not is the hardness of the material. If it's soft, it's of course not going to feel like it's sharp. But then the important one is, it's the same analogy as like the snowshoe, right? If you step on snow, you're going to go right through because you've got all the force, all 165 pounds of myself stepping on it, it's going to go right through the snow. If you disperse that same amount of 165 pounds across a bigger area, it's actually less pressure on the snow itself and it won't fall through. The same thing happens with the scalpel. Again, it's counterintuitive. People think you're sharper. You're making it sharper. Oh, it's going to go through. It's going to cut easier. It's actually the exact opposite because what we do in our brains, we always thought about pressure and force is the same, but they're actually different physical measurements. So the force is what the surgeon pushes down on the blade. Pressure, there's a certain amount of pressure to penetrate the skin. Pressure is that force divided by whatever the area is that it's coming in contact with. So with this, if you think about a standard blade, so we flip them up, you've got essentially like a serrated blade that's coming down, so you've got these very sharp, if you will, or jagged points coming down, just to make math easy. Suppose you've got 4 points and 10 pounds of pressure. Okay, so you got 2.5 pounds of pressure on each one. With our blade, it is so smooth that entire area is coming in contact with it. So it will feel, or can feel in some circumstances, like it's duller because it's just purely the physics. There's so much more is actually touching it. So that's kind of the adjustment that you have to make. And some surgeries, they don't feel it at all because it doesn't take that much force to begin with, so they don't see anything. Other ones they feel, right? Like Dr. Bernasek, I think when the first time he used it, didn't you say, he was like, I had to put too much pressure on it. And then he used it again, and he started realizing, okay, here's what I have to think about, and that's the adjustment cycle. But there's also some things we can do to even maybe improve that a little bit. We've got a couple different ideas. But as we hear from you guys go, yeah, I love it for this, it sucks for this, that's when we can start making, okay, what about it sucks? And then we can start making some changes and adjustments to it so that you have a blade that is really, truly an ideal blade for whatever it is that you want to do. So, and again, blade is just the first thing. This technology can be used on anything else that you guys have for medical devices. So as long as the material is hard. So here's just showing an example. You know, the area of the standard blade is always going to be less than the area of the Planatome blade touching it. And if you know, this is probably not that far off either. So if the area of the Planatome is 30% more than that, well, the surgeon's going to have to put 30% more pressure down. And that's about what we hear is.
Yeah, well, and it was amazing because we actually got data to support it. But when we went to that first cadaver lab that Tim was showing the videos of, you know, the doctors were using it and they said, yeah, it feels like I've got to put a little more pressure. I said, well, can you quantify it? He said, that's probably like 25, 30% greater force. So we set up a force penetration fixture in our facility, and it came out, it was like 130 grams versus 100 grams to penetrate, and this was with pigskin. So
the physics hold true.
yeah, physics matched up to what, I mean, it just shows you how perceptive surgeons can be with what they're
Just
doing.
the feel.
Yeah.
It's remarkable, you know,
Yeah.
how well tuned your hands are to those minor differences that are in there. So, anyways, that's kind of what to expect, right? You go in, you're not going to feel the click, click, click. You might have to put a little bit more pressure, and some things that you do, you may not feel anything different at all.